We'll introduce the topic of alternating current in this chapter, and then later we'll talk about alternating current, and we'll discuss why the United States has alternating current. Actually, why the whole world uses alternating current to distribute power to homes and factories and things. There's an important reason why, but we'll introduce this concept here of alternating current. So let's take a wire, section of wire, and I have a current flow in one direction. And after a certain amount of time, we flip the direction of the current in the other way, and then we flip it back, and we just keep in this cycle of flipping the current back and forth. And the charge doesn't really move, it just keeps oscillating back and forth. If I have my red pin here to represent a charge, it's just bouncing back and forth. It's not really going anywhere, just kind of sticking there. And if we look at this graphically, if I have a graph for the position versus time, you would see normally a sine wave. As the change in position over time. Now, this also works for potential. You'll see the potential change in the form of a sine wave. You'll see the current, the value of the current, the rate will change in the form of a sine wave. So that's one possible. You could do a sine wave. Another possible way of doing it is you could send out a square wave. That would be considered an alternating current. You could do a triangle wave. You could do a sawtooth. You could have this go up and then drop, and then up and drop. So alternating current just means that it is changing direction. And in some cases too, you can look at alternating current as being pulses of DC. So the current actually doesn't actually go backwards in the strictest sense, but we can use the same kind of analysis when we talk about these changing currents. We can talk about them as far as alternating. Now, one measure that we need to understand is root mean square. And this root mean square, it's represented or abbreviated RMS, and it is the effective potential to produce the same amount of heat in a quantity of water. And so basically it's the amount of energy to raise 1 cubic centimeter of water 1 degree Celsius. So let's take a look at a sine wave. That's a terrible drawing of a graph. And so I have a sine wave, and the current's flowing back and forth, but it's not constant. And so if I want to be able to get an effective value, so here's my peak, there's my voltage peak there, and I want to know this effective RMS value. So the voltage RMS represents the DC voltage equivalent. I think I spelled that right. So if I were to put a DC current at the value of voltage RMS through a resistor, and I put this sine wave through the same resistor, I should get the same amount of heating based on both of those. So how do I find the voltage RMS based on a voltage or even a current? Well, it's defined by exactly the way it's called in the reverse direction. So for our voltage, RMS is equal to the square root of 1 over the period integral of from 0 to the period of my alternating voltage squared times time, differential time. And that's all in there. So if you look at this, there's my square. This is my average or my mean. And this is my root. It's just the process in reverse order. And current will have the same form, like so. So let's do this for a sine wave. So we have Vrms is equal to square root 1 over the period times the integral of 0 to the period of A and the amplitude sine 2 pi frequency t, standard sine formula, squared dt. Well, this is in terms of frequency. I'd rather have it in terms of time, of the period. So that's just going to be the square root 1 over t, integral from 0 to t, amplitude times sine of 2 pi over big T times little t, squared dt. And now I take the integral and I get the square root 1 over t, a squared, and the integral of sine squared is t over 2 minus big T times sine of 4 pi t over big T, and this over 8 pi evaluated from 0 to t. Okay, so now we need to put in our limits. So I'm going to have t over 2 minus t sine 4 pi times big T, substitute big T in for little t, over t divided by 8 pi. Put 0 in for the first term, that's just 0. And then I'm going to have minus a minus is going to be a plus t sine 4 pi times 0 over big T, and that whole thing over 8 pi. So we have 4 pi times big T over big T. The big T's go away, and the sine of 4 pi is 0. So this whole term over the period averages out to 0. And in this term, the last one under the radical, I have the sine of 0, and this term over the period goes away. And now I'm left with square root of 1 over t times a squared times t over 2. And that just simplifies to a squared over 2 and that's just equal to the square root of 1/2 times a. Actually, I should put a in front of the radical. Or you can simplify that to be a times the square root of 2 over 2. This is the voltage RMS, or the DC voltage that would be the effective value. Now there's graphs in the in the presentation to basically show graphically how that works, but I'll let you look that up at a later time.